Hello, this is Physics 103. This is on atomic structure. In this lesson, we will learn about the emission spectra of hydrogen. So we have discussed Bohr's planetary model of the hydrogen atom, wherein the electron can only exist within permitted orbits. And we also know that the electron can only have quantized values of energies depending on the integer n. So now we ask, what happens if we say give an electron an energy in the form of light, and it is to transition from, say, the ground state n equals 1 to the excited state n equals 2. So we are to ask, what allowed energy of the photon can the electron absorb for it to go from n equals 1 to n equals 2? So we know that the energy of a photon is given by Planck's constant h times its frequency f. And we will equate it to the change in energy, or delta E, for the electron. So we write hf to be h times c over lambda. This will be equal to the final energy of the electron minus its initial energy. So this is the energy required for the electron to jump from one state to another via shining a photon on it. Okay, so let's write this energy. So this will give us hc over lambda equals minus me to the 4 n final square epsilon naught 8h square, and then minus the initial energy of the electron. This will be n initial square epsilon naught square 8h square. So notice in our expression for energies, this term is constant, this is constant, and they are all the same. So it only varies by the quantum numbers nf and ni. Sorry, these are not quantum numbers yet. This is just an integer in Bohr's perspective. So we can remove these constants and just retain the integers nf and ni. So we have hc over lambda. Okay, so I will take out a positive sign here. So this will become m e to the 4 epsilon naught square 8h square, and then we will be multiplying it by 1 over n I square, then minus 1 over n f square. So notice that the signs are reversed here. Okay, so now if we are only interested in determining the wavelength of the photon that is to hit the electron, we will bring down these terms h and c to this constant. So we have 1 over lambda equals m e to the 4. We will have here epsilon naught square 8. Now h will be cubed and we will have a factor of c. So this will be 1 over n I square minus 1 over nf square. Now, this term, the constants in these terms can be simplified into a single number. So we call that single number the Rydberg's constant. So it is denoted by R. So R over 1 ni square minus 1 over nf square. So this is Rydberg's constant. So Rydberg was a physicist and he was credited for his pioneering work in the emission spectra of hydrogen. That's why it's called his constant. So R has a value of, let me check, 1.097 divided by meter. Okay, now so this equation will tell us what is the wavelength of the light that is needed so that the electron can jump from an initial state to its final state.